Hi, everyone. So we're the Antarctic Ripples team, and we'll be talking to you about some of the results that we've investigated over the last several days. And I just want to firstly note that while we didn't have any conclusive scientific results, we learned a lot about the methods, and that was a large part of our goal this week. And we're excited to share some of the preliminary results that we found with you. So we hope that you enjoy that. Sorry, I'm having some technical issues. Okay, here we go. So our project mainly focuses on this one site called Hercules Dome in Antarctica. It's about 400 kilometers from the South Pole. And it's a potential location for a deep ice core site that targets Eemian ice about 130,000 years old. I personally am involved in the geophysical survey of this region, which has lasted the last few field seasons, kind of to varying degrees due to the pandemic. So the question of our project mainly really stemmed from kind of when I was out there with some of my colleagues from the University of Washington, kind of driving our snow machines around. We noticed that there was a distinct difference in the surface roughness across the dome. You could kind of see the surface topography of Hercules Dome on the left-hand side here, this kind of like L-shaped region. And we noticed that there was a noticeable difference. So the northern grid north, I should say, part of the region was a lot smoother, and the grid south region of the divide was much more rough. And these are some photos that that we took while we were out there. You can kind of see that, although the scale is kind of hard to see in the pictures. Yeah, I guess I could just kind of wanted to show this as a motivation. The right-hand subplot shows this kind of surface roughness along one of the radar lines, kind of in the southern region of Hercules Dome, and you can kind of see that we can see this kind of Sistergi scale 10 meters maybe at the most scale of features along the dome. And so really this, I guess, made me think about surface roughness and how that can modify the atmospheric exchange in the near surface firn and affect the chemistry preserved in the bubbles and ice cores. And so that was kind of an interesting kind of question of, can we characterize this here? And so our project here during the Hackweek kind of focused on, can the ICESat-2 data kind of confirm our ground observations, and what can we determine about the spatiotemporal variability and roughness from these data? Yeah, so I'd also like to just briefly note that that we also were hoping to look at other areas such as blue ice areas where surface roughness also has different implications on the science there, but we didn't quite get to that. And yeah, I guess with that, I'll pass it on to, I think, Veronica.
Yeah, indeed. So I will talk a bit about the methods. Basically, there are different scales of roughness within on the surface. So in the beginning, we thought of looking at different areas. So not only in Hercules Dome, but also in blue ice areas. And there, I think it's even more pronounced that you have bigger ripples and smaller ripples at the same time. Basically, there is so-called small scale roughness. So that's sub the footprint size of ICESat-2. So it's on very small scales. And for the there's also bigger roughness patterns that are larger than the footprint size of ICESat-2. So for these two types of roughness, we took two approaches. I will highlight the first approach, so that's for the sub-footprint roughness, and then later we'll come back to the other approach, namely the spectral analysis to find roughnesses on larger scales. Could you go to the next slide, Annika? So basically what we did is that we used the RMS misfit of the slide rule. Basically what slide rule does is you select a segment of 10 meters, or that's what we did. You can adjust the length, and then it estimates the slope in this small segment. It also returns the misfit of all the photons within this segment. So it's just the distance of every photon to the estimated slope. And so in this RMS misfit variable, if the surface is rough, this RMS misfit variable is larger. But also if there is a sloped surface, the RMS misfit will be larger. So you can express it in a formula that Ben invented during brushing his teeth. Could you go to the next slide, Annika? So what we expect to see is that the variance of the received photons is dependent on basically the instrument noise, so the standard deviation of the transmitted pulse, the variance of the surface, so that's the surface roughness, and the surface slope. And this is a bit indirect because that depends on the width of the footprint. So if you would have a footprint that's infinitely small, then you wouldn't have to consider this parameter. But if you have a larger footprint and there is a sloping surface, then some of the photons come back from the lower part of this footprint and some of the higher part of the footprint. And so you see that back in the variance of the return signal. Can you go to the next slide? So this is just to illustrate what I explained before. These are two little parts of one reference ground track. It's 1 kilometer along track, so it's really a small part. And on the left-hand side, you see the measurements in the south area. So you see it's the slope is going up. And on the right-hand side, it's the north area, and in general, the slope is going down. But these slopes are really small. It's just 2 meters over 1 kilometer, so that's very small. And then I plotted the RMS misfit as error bars. So you see this kind of white region around the track that should be strongly correlated to the surface roughness. And then I'll hand it over to Ben from here.
Okay, so we began by just drawing 2 boxes on the map and extracting the RMS misfit parameter from all of the slide rule segments that we found within those 2 boxes. And we got an initial promising result just by making a histogram of those RMS misfits. So we have here the histogram for the north box and the histogram for the south box. Remembering, of course, that these are grid north and grid south. So south is north and north is south, but we won't belabor that point too much. And we see that the south does, in fact, look slightly rougher than the north. So the next step after that, next slide, please. I think I'm taking this one too. This is actually something that Annika put together. was to divide the area into 5-kilometer boxes and calculate the median RMS misfit for all the segments that fell within each of these boxes. And we did this for, are these cycles, Annika?
Yes.
Yeah, so for cycles between, it looks like cycle 3 and cycle 11, 12. Anyway, you can see that there's sort of a general pattern here where in the southern box, it's a little bit rougher than the northern box, or I think maybe a better way to say it is that the northern box is really, really smooth, and a lot of the rest of the grid can look quite a bit rougher than that. And I think these plots also suggest that driving further south than Annika did might have been sort of an unpleasant experience, because it does seem to get even rougher as you go farther south. But it's nice to see that there's sort of a consistent signal here from cycle to cycle. And even though there are some cycles that look a little bit different from the others, the spatial pattern is generally pretty consistent. Can we go to the next slide? So this, I'm going to pass this one off to Manjaree, who was looking at what makes for consistent estimates.
So basically what I was trying to do was look at the data quality, what we were getting from the slide rule, and what we define as strong beams were the number of photons is greater than 100, and so we just plotted it for the north box and the south box. But what we see is there are some outliers for the like around 350 and 500 for the south box. So we still don't know why they're there or what scientific reason, or is it just like some error? So that's something we still need to look into. Can you switch to the next slide? I think I'll hand it over to Regina now.
All right, so having looked at sort of the sub-ICESat footprint roughness, we also wanted to look at the roughness over larger scales. So I took an approach of splitting up the ICESat tracks into segments of 5 kilometers and just looking at that along track profile and doing a spectral analysis on it to see if I could get a sense of like what the signal strength was at each spatial wavelength and the overall sense of roughness. So on this slide on the left is sort of just a random sample of along track profiles. You can see they're detrended. They're still mostly pretty flat. And then on the right side is periodograms of the signal strength at each spatial wavelength. Next slide, please. And so on the left here is an attempt to translate that into sort of a scalar measure of roughness at the midpoint of each of those along track segments. And so I put up a graph also of the gridded small scale roughness from one of the previous slides, just to show that there does seem to be some correlation between, at least just visually, correlation between the large scale and the small scale roughness. Is that actually something we expect to see? I'm not sure. That would be an interesting point for a literature review. So it does seem like we've got some sense of what the roughness around here might look like, both at the large and small scales. Next slide, please. So we've got this general sense of how bumpy everything is, and future work. One obvious direction to go is we would like to test out these methodologies by comparing them with in situ observations from GPS or any other measures of surface roughness that are available. We as Annika, I think, mentioned, we would like to expand these results to other areas of interest, particularly blue ice areas, potentially areas that have melt. Both of those represent some potentially more complex issues with signal interpretation, since blue ice areas won't have such a well-defined surface, since the photons can penetrate into them further. Areas with melt, water obviously creates its own tricky problems. But I think that would be another nice place to go with this. And we'd also like to look more at these sort of roughness along a time series and get a better sense of how those things vary. Maybe what are some sources of noise and signal in a time series, and how can we better understand what processes are driving this and what processes it might drive. Thanks to the whole team for an excellent week. This has been super fun.